what we're going to learn about today, and it's about time, is to make contact with experiment. To talk about anomalous dimensions. And time permitting, we'll have at least a few words for it, operator mixing. And we'll try and bring everything together and give a prediction all the way connecting the infrared and the UV for one of the models we matched onto. But to do that first, we have to go through yet another computation. We're not afraid of loop computations now, and there's quite a few in the notes. I'm not going to go through all of them. I encourage you to go through, but the one we're going to look at now is the other divergence from C6. Remember, C6 has 6 legs. We looked at that diagram the other day, that octopus-like diagram that gave a contribution to lambda. It's infinity, but we add a counter term, or we change the renormalize lambda. And today we're going to look at this other one, in which there's another insertion of lambda on top of C6. And now, alert check. What is the operator that this will produce, do you think? We had, well, not enough notation, but it's x6, xg, and s. There were actions for a non-derivative term and 2 derivative terms in there. If I just look at this from the outside and put a black box in here, which of these 3 operators do you think that contributes to? I hear 6 there in a low voice. Yes, x6 was the only one that from the outside looked like 6 legs. These guys look like 2 legs with momenta in them. So this is going to contribute back to itself. So that's going to be its own renormalization that we're looking at. But then if we're doing this with diagrams, and we'll first of all, we'll do it here with Feynman diagrams. There's a problem in the notes to do with functional methods. With diagrams, we are using complex fields, so we have to put arrows in here. Alrighty, so there's 2 possibilities, and this will be associated with ST channels, but in here it looks a little different. It could be that the arrows in the loop, one of them is, remember these arrows are for the complex or for the mission conjugate or the field itself, denoting. So it could be that one comes into the vertex and one goes out. In that case, well, let me put the prefactors. So those will come with I minus I lambda fourth. And there's going to be an I C6 over lambda squared for the other vertex. There's going to be, you see there's 2 propagators and an integral over momenta. We can neglect the momenta flowing through those propagators because we're interested in just the UV divergent piece, but it's not always the case that one can neglect them. So there's 2 of these squared. And now times. This first diagram we drew, well, I'm afraid we're going to have to do combinatorics again. So in here, the outside legs will be coming in, out, in, and out. And in here, will be in and out. Again, the internal combinatorics first. I take any of the legs for this 6 point, or any of the 3 legs coming in. There's 3 choices there, and there's 2 legs coming in for that other one. So 3 times 2, 6. And the same thing is true for the leg going out of here. 3 choices in there. It's a separate set of legs with 2 choices there. So another 6. Then there's these other 2 diagrams. Let me do this right. So there's two arrows going in the same direction, and then so we have to come out. This is, remember, this is a conserved symmetry, so these arrows can always, the flow has always got to go somewhere. So if there's two arrows going that direction right, they will also come out through the right. Whereas in here, there's four vertices, so two might be going in and one in out. And then there's the same one with the arrows flowing into the higher dimensional operator. Well, if you do those combinatorics, you get another 6 for this and another 6 for that. Right, any of the three in here has 2 in there, but then there's only 1 left to connect in there for 2 other choices in here. If you don't like combinatorics, again, do it the functional way method. You don't have to worry about that in that case. So what this looks like after all of that is said and done, again, this is a loop integral in DIMREG, but you can go to Anish's notes or any reference with DIMREG integrals like, or if you up for it, take the full definition in terms of gamma functions, expand in epsilon, blah, blah, blah. What you get at the end of the day is a collection of all of those terms that I'm going to write it already in the form of a, oh, sorry. So that's the internal kinematics, and the external kinematics will be how to assign 3 legs for incoming, 3 legs for outgoing. So I know there's 2 factors of 3 factorial for those. Right, but those factors of 3 factorials were also there when we derived the Feynman rule for the vertex. So if I now translate this back into an action term, we'll have the original C6, well, actually comes out, C6 of lambda square was there originally. What that looks like effectively is another contribution. Effectively is, I mean, if you put a black box in here, all you know is a 6-point amplitude and local. That divergent term is at least, and there's the 3-level contribution and the one we just found. Once you put the signs in, it's going to be a single 3 factorial term because the other 2 are common to the 3-level. 1 over 4 pi lambda, 1 over epsilon, and this log of mu square over k square, where k square is just a placeholder for the energy at which we're doing this scattering, if you think of it. Right, with the term outside, pi star phi cubed. Once more, there's a divergence, but we change the name of C6 to some C6 renormalized to cancel only the 1 over epsilon. We're left with the log. The relation is, I mean, you can read it from the equation, just whatever it takes to cancel the pole. What it takes is the prefactor. Let's think about it. There's the original term was a dimension 6 operator that needed a 1 over lambda square to make it dimension 4. This contribution has 2 vertices. One of them comes with C6 over lambda square, and the other one is lambda. Just dimensionally, that already works out. It's a 1 over lambda squared. That will give me the right dimensions in there. The leftover piece is lambda, which is dimensionless. Little lambda, sorry. This is, well, you know what I'm talking about. It's just in the audio, it might be unclear. But yeah, it has the right dimensions already. And you can work out those dimensions as to where was my operator coming from. Your operator was coming from dimension 6. What is my operator contributing to? Again, the black box will tell me that it's contributing to another dimension 6 operator. So I don't need any insertions of scale. The other case we looked at was dimension 6 contributing to dimension 4 without these 2 legs. And then you do need an m square to make things work out dimensionally, but also explicitly with the computation. Righty, and so the problem in the note would be would allow you to do this in functional methods for a general phi n of instead of just 2 entries, as many as you want, and as you correctly pointed out the other day, for n equals 4, you can reproduce the standard model normalization of or running of CH is related to that prefactor there. So that would be, let me tell you. You can call this prefactor that shows there, that will be minus gamma halves, for reasons that we'll see in a minute. And for n equals 4, you'll find that gamma, if we borrow it from that reference by Anish and collaborators, that was 108/4 times lambda. We also have to convert what they call lambda to us, and this, I should also say, this anomalous dimension is also to be found in other papers. Other people were working on these RGs, including Alex himself. But yeah, you can sort of see what is this 108 funny number doing in here. Well, what's doing in there is coming out of that computation when you set n equals 4. All right. It's a power of, whenever you find a number like this in a theory, you wonder how did this come about from our original theory that didn't have any even factors of 2 or anything about that. So this is a product of doing the computation. Righty. So that's just computing, but any questions about this? No? Good. So now is the promised contact with experiment. All right, very good. Epsilons here and there. The first problem to address is cancel those infinities. Now a physical prediction gives you infinity. Now that we've done that, there's the essential step of connecting these two experiments. Now, just for concreteness, envision an experimentalist that has a collider machine where they have, say, a phi, anti-phi colliding. Whatever happens here happens. The experimentalist doesn't need to know about that. They just measure the outcome. And in particular, they measure the production of two extra particle anti-particle pair. And somehow, I mean, it's not as simple as this first cross-section stuff. There's also going to be what we call non-local terms with propagators. Let's assume somehow they have, I don't know, an angular observable, some way to tell apart only the contact bit in there. And so somehow they've managed to measure their invariant matrix element M. Again, they will measure cross-sections, not that, but I don't know. This has to be simplified somehow. So they measure that local matrix element, and of course, that experiment is happening at some scale. Let me call that KIR. So that matrix element measure experimentally, this is a number given to us by the experimentalist. We have computed a prediction for that coming from that term. And it's just recycling what we wrote in this. It's going to be 3 factorial squared over C6 renormalized with all those infinities gone. And with our definition, let me call this extra piece minus gamma halves of logarithm of mu squared over K pi r squared. Right, and this is connected, or will be connected to the reason why this mu scale that was introduced artificially in DIMBREC and was unphysical will eventually go away from our expressions. When we actually do predictions in terms of other experimental predictions. For all of the talk and computations and everything we've done, we haven't made contact with experiment yet. So you have to tell me, you have to give me some reference point in your experiment to tell me what my parameters are. Once I fix them, now I can make predictions for other processes. So for that matter, let me define a function of this original matrix element measured by experiment. Let me define C6IR over lambda squared. Remember, I'm separating in C and lambda squared, but you only measure the full thing. And that's just this M local KIR over the 3 factorial square that I don't like. Which at the same time, it will be the same as this theory prediction, C6 renormalized lambda squared 1 minus gamma log of mu over KIR. I've just taken a factor of 2 out to get rid of that a half. And then I have an expression. I want to substitute my C6R in terms of this measure C6IR. So just plugging it back into the general expression for a matrix element, now evaluated at other different K. I'll simply have C6R is 1 over that. It will be C6IR over lambda squared 1 minus gamma log of mu KIR divided by 1 minus gamma log of mu. No, sorry, that's a general expression K, and this is KIR. Alrighty, but this is, again, we're doing things to the one loop level. We can expand that denominator in there. And that will give us IR lambda squared. You can sort of already see that log of mu is going to cancel out to leave us 1 plus log of kappa, or k, sorry. I don't know my own notation. There will be here order gamma squared, but I'm secretly gamma, or not secretly, openly. Gamma is a loop correction, so we're only working to one loop. That's going to be the next that we can forget about until we decide to do a 2-loop computation. And so voila, the mu scale has disappeared once we make contact with experiment. What's more, we can now make predictions for that same local term at a different scale k. And the effect that we've computed, I should say we've computed a one-loop effect, but we're focusing on those UV divergences that will give us logarithmic dependence. There might be also constant pieces that we assume are smaller than the logarithm, but also those will get swallowed up in this definition of C6IR. Another prediction we can make is that if I repeat the experiment at higher k, the expectation will increase logarithmically, and we sort of found what gamma was in here. Minus gamma was minus that, so gamma is positive. In our case, gamma is 4 times 3 factorial over 4 pi squared lambda. So we have the prediction that the coupling will increase with energy. And if we're doing, in particular, experiments only at low energies and we're not interested about high energies, this is good enough. We have our prediction in terms of observables, and we can, like I said, we can now make predictions now that we've made contact with experiment. Alrighty, so we've seen what all of this whole sort of randomization at the end of the day turns into a logarithmic dependence of the scale, the actual physical scale of the observables we're looking at. Righty, questions about this? This is gamma at one loop level, but there will be corrections there. It includes lambda, yes. Yes, you can do a little better, but yeah, that's what we're going to do for this lecture. But if you want to be consistent, there's going to be a set of RGs, and this guy comes with its own. So it also that's in there, but I don't want to say that because for this, that is a problem for you guys to do. For this lecture, we're going to consider it as a constant. Okay, and then you can do a slightly better. But good, any other question? Okay, that is the fruit of our labor. Our hard loop computation has told us what is the coefficient in the log. Okay, and once you've done it once, you can sort of do it faster other times. Yeah, that's what we're saying, that this lambda here is itself mu. So in general, what you should have to be consistent and stick to one loop, you should consider the RG of every one of your couplings with gammas computed at one loop. And because this is going to be a coupled system in general, this depends on that. It not always can be solved analytically, but at least the procedure is clear. And I'll summarize this by the end of this talk. But yeah, you first you compute the gamma anomalous dimension matrix, which you can think of it as a bigger matrix at one loop, and run it to whatever scale you want to. Well, you first make contact with the experiment, then run. There's the other option. This is what we'll do by the end of this lecture. If I am a theorist and I have a prediction for the UV scale, then the running is the other way. I match at the UV and I run down to the IR. And that's what we'll do by the end of this lecture. Right, any more questions? Okay, so now we're going to actually write those differential equations. We haven't done that yet. We just seen that is the prediction. And in fact, a good one if you're staying at in the IR and you're not moving much, so that logarithm doesn't get too large, then this sticking to this order is a good approximation. But if you want to connect with higher energies, you might have to worry about this log getting large, and that's where the RG becomes useful. But just to tell you, now we can look at anomalous dimensions. This is part C. And the basic observation is, well, that mu was sort of a proxy, an intermediate, a mediator to the final answer, which tells me that any physical observable, once it's expressed in terms of other experimental inputs, should not depend on mu. So I can just use that from the beginning and say, my original prediction shouldn't depend on mu to this order. And then I'll have T6. Let me take lambda squared. It's a bit arbitrary who depends on mu, but that can be my convention. And say that the derivative with respect to mu of CR plus the loop correction, which I've called log mu over k, is 0. Sorry, that's 1 plus. Oh, sorry, with my definition, 1 minus gamma. That will be a differential equation for C6. If I take it over to the other side, gamma, well, the log of mu disappears. And there's also that extra term minus log of mu over k. But again, we work into one loop, so we can neglect that. I'm being a bit careless about the subindex of C, but it won't affect the result. Now we do have that RG that I've really talked about there. That is precisely gamma. That's why I called it that. And the way it looks like, at least for this simplified subset, is nothing too hard to solve, is that the derivative or the logarithmic derivative is proportional to itself. If gamma is truly a constant, which is not, if I will take it to be 1, I can solve that pretty easily. But before I do that, I should know what to do with it. So let's first solve it for perturbatively. So if I assume that gamma is small, which is again a good approximation for sticking to low energies and doing all just measurements there, we'll have that C6 of mu is some C6 at some reference scale mu naught, plus a correction will be just gamma C6 mu naught of the logarithm of mu over mu naught. If you want to use t instead of log of mu, that will be that c at any scale is c at a fixed scale plus t gamma, the original value. I put this back into that original equation, and it will do its job. Log of mu will cancel with that other log of mu. Again, I'm sticking to one loop, so I neglect higher order. So what that will give me is C6 some scale mu 0. In our case, that was KIR plus gamma, the logarithm of mu 0 over K. Sorry, this is very rudimentary algebra, and I'm checking twice what I already know will happen. What I want to rewrite this as, and that is the non-trivial bit, is that I can think of that as the integral from mu 0, or from some scale mu 0 to some scale K, dc6. Because this is dc6. Or if you want to write it mu with a chain rule, however you want to write it. So what we're doing in here is treating mu as a dummy variable we integrate over to get from original scale to high, low. In fact, writing it as a differential equation. Also, I'm putting those boundaries, the boundaries of that integration are the two values we measure at. Then we don't have to worry about whether it's at the high energy and go to low or low to high. All of that is taken care of by putting the boundary conditions in that equation, so to speak. Good, so now we can actually solve that equation in generality, well, assuming gamma is constant again, and apply this procedure, integrating from whatever scale I start to whatever scale I want to end, to make a prediction. And now I am going to do it. And now I'm going to do it the other way, from the UV to the IR. But again, all of that is taken care of by putting in the boundary conditions, or the initial conditions, rather. So let's just solve that equation. Which equation? This equation. dc6, I can separate variables over C6 from some scale at the UV, that is lambda. Can you see that? Lambda to some scale K. That will be gamma is truly constant, g mu over mu. Sorry, differential equation. This is C6 in the UV. And then this is C6 at K. Just like X of T, and this is from lambda to K. Sort of the initial condition in here is that C6 at lambda is C6 UV. And this we have computed in the second lecture. All in all, this is, okay, let's see if you can see it. And this may be too hard a question, but can you solve this in your head? It's not so simple, so I want you to suffer for a little bit and then I'll give you the answer. Well, if you have 2 minutes in a piece of paper, you'll do it. But in your head like that, it's not so easy. But anyway, a log here, a log there, but with a different proportionality constant, right? So I'll just write it. Log of C6 over C6 UV is gamma log of K over lambda. Now I exponentiate on both sides, and I get C6 is C6 UV, and the exponential of this with that gamma will just give me K over lambda to the power gamma. Alrighty, and now we can, so what I've managed to do with this, solving this differential equation is connect the UV and the IR, meaning some K in there. And this is now not approximated to one loop. We've used the power of the RG to, in fact, resum a lot of leading log terms in here. As it happens, that gamma is a number that is pretty small. If it's a small number, you can expand this exponential of e to the I epsilon log will be the log, and you recover that. But this is the solution in general. And I can do a bit more if I want to connect this to, say, we didn't have time to go through this in the lectures, but the ADS EFT connection gave us the C6 operator only. And we've seen that this C6 is sort of only produced at the renormalized at the loop level. It only produces itself, so it doesn't produce any of the C6 CG, the other two operators. So this will be a consistent prediction. For that case, we'll have, let me put back in the lambda square. This is the Wilson coefficient that we measure. And in that case, the prediction will be K to the gamma, lambda over gamma, lambda squared. And C6 in the UV, well, I'm going to write it in terms of other parameters of the model. You might not remember what these are. Something to do with the extra dimension in the ADS picture, or the dimension of the CFT operator you coupled to. Point is, that's a prediction from the UV model. And all of this comes out to be a dimensional test coefficient. And here's when the EFT packages your UV information and some Wilson coefficients. That is what the UV tells me. In this sense, it's an initial condition. Whereas the RG that we can compute in the IR is giving me that exponent there. Now that we wrote it like that, another question about your intuition. Why do you think we call gamma the anomalous dimension of the coefficient. Where do you think that inspiration came from? Again, it's not an easy question, but let's try and see if you can make sense of why it is called anomalous dimension. That's right. We said in the beginning, these operators are dimension 6. They should come with 1 over lambda squared, and at the end of my computation, I'm expanding in 1 over lambda squared, etc. Whereas, and I look at the final prediction, and that coefficient comes not with 1 over lambda squared, but with an extra power of gamma in there. This is now not an integer. Of course, it's dimensionally correct because there's a lambda downstairs and a kappa upstairs. But we found that the way the operator scales and the prediction scales, the physical observable scales, is with an extra correction to the naive classical dimension of the operator. Right, that was a nice story to tell in that sense, taking gamma constant and borrowing your intuition. Now, like I said in the notes, there's problem 5a, where I ask you to also consider that the lambda itself runs as b0 times lambda squared, and yet another problem is to compute that b0, but that b0 is a constant, now truly a constant. So I ask you in the notes to take the same RG and basically change variables with the chain rule from mu to lambda, and then you can solve C6 as a function of lambda. At both the UV and the IR scales. Alrighty, so that's a nice, as it happened, we chose a particular operator that has some special properties. It's a standalone operator. If you start with in the UV, the only thing in the IR one loop that you'll get is that same operator rescale. It's a particularly simple example for us to understand and bring together everything we've done, from the matching to the equations of motion to the renormalization. Here's our prediction connecting the UV and the IR and the whole. That's the top-down program of EFTs. And that's, for example, the program you use for B decays, connecting the standard model prediction and the electroweak scale, giving you that UV coefficient, then you run it down to the B meson scale for it to decay with those predictions. What we're doing at the LHC now is a combination of both. If you're a theorist and you know you have a model for predictions that has a scale above the LHC, you compute your CUV for your theory, and then you run it down to the scale where the experiment is measured. In fact, we've done this for quite a few years now, and there's code that automatizes a lot of these things. Or if you're a bottom-up, as some physicists are, instead you always live in the IR, you have your operators, all of that perturbative expansion in the logs is actually perfectly under control if you always live in the IR, and you simply consider the most general set of operators and the signals that they could produce at the LHC. And say one day we get a signal at the LHC for that we can identify as a higher dimensional operator, we can run this process backwards. We can say, okay, we've seen this at the low energy. It's a differential equation that goes both ways. If I measure this at this energy, what would it correspond to higher energies? That is more related to the inverse problem that I think was mentioned in another setup. They were thinking of SUSY now. That same thing happens here with operators now. Good. So in the remaining 15 minutes, we'll say a few words on operators mixing and the rest of contributions to that anomalous matrix. But before we move to that, it's probably good to take questions about this. No? All right. Good. So, well, it's good that we managed to reach that connection and sort of bring things together. But we started with a with a 3-dimensional space for the EFT coefficients, and we've only computed the diagrams associated to C6, either to the renormalizable part or to itself. And perhaps it's not clear to see, but we've computed or looked at all of them, and none of them produce the other 2 operators. The ones that could have would have been those without the 2 extra legs, but after doing that computation, no momento came out, so it was only a contribution to lambda, not to the dimension 6 operator. So these are the leftover diagrams we had in there. One of them I set up as a problem for you to compute, and that's, Alex was talking about mountains to climb. That will be the highest mountain to climb in this set of lectures. It's a computation that requires not approximating the denominator coefficients to not depend on momenta. You have to do those integrals with Feynman parameters. You have to then match onto operators. You might have new operators appear that weren't there. That's possibly more than one evening to do that. But in here, we're going to just sketch what those diagrams will give us. So let's look at operator mixing now. If that was C, this is D. There's 3 types of diagrams left over. All 3 containing that other type of operators with 4 legs to derivatives. One of them, relevant for what we're thinking of, will look like this. 1 higher dimensional, 2 lambda. So let's try and think about a matrix. Where would that go? So we said now that in general, there's going to be a matrix of anomalous dimensions rather than just an entry. And if I put it into a vector, C6, CS, CG equal to a matrix times those same coefficients. S, CG. We have seen what is CS self-renormalization, so we know this entry, and we've computed it. Any other entry in that matrix, we know what value it takes. I'll give you a hint. We've computed, the previous section was called C6 proportional divergences. And we computed all of them. The first column, almost. So we said that everything that is proportional, remember, where do this gamma matrix comes from? It comes from looking at those UV divergences. This is on the right-hand side. And we computed all the loop terms that were proportional to C6. C6 renormalized itself, but also it didn't produce any of the others. So actually, we already know that these other 2 are 0, because C6 doesn't contribute to CX, and C6 doesn't contribute to CG. Right, so we knew more than you thought. There's still 6 entries left in there. What would this, let's assume this is C6, CS. What entry would that correspond to in this matrix? will be this one indeed. That will be C6 contributing to 6 coming from S. So I'm going to put a bar in there. And the rest of entries, well, I think this one, the contribution from CX to, no, CG, sorry, from CG to C6. We haven't shown this, but I can tell you that if you put it in here, CG, it cancels, and you can see this because we defined this antisymmetric matrix for CG. There were sort of goldstones and sort of a quick but yet explicit writing of that amplitude, that loop correction will convince you that it cancels. So that's another exercise. So that's, we have no gamma bar in there, we have a 0, but that doesn't mean that that entry is 0. And then we'll have the other entries to compute, you know, CSS, gamma GG, gamma GS, gamma SG. But computing this, and it's actually, is it? Yeah, well, computing this will give us 1 over epsilon times CS. That will contribute to C6. That's what we said it comes in there. So we'll have to renormalize C6, or just add one over epsilon terms in C6 to cancel that divergence. Repeat procedure, find gamma, put it in there. The other type of diagrams that we have left have less legs. Let me just sketch why one of them we don't have to worry about at this order. There's also going to be this term. What is this going to affect, you think? Yeah, so this entry will be proportional to lambda squared, because there's 2 lambdas in here. So I didn't put it in there. It will be, you know, lambda squared over 4 pi. Yeah, but the powers of lambda will be different for different entries. It's not just 1 power of lambda. You see in here that it's lambda squared, but the one we looked at is lambda. You can work those lambdas as well, the powers, but it's not true that it's going to be linear in lambda for all of those. Mm-hmm. Yeah, that's got its own differential equation. So if you want to do the procedure there, you can, instead of write this as a differential equation in terms of mu, you could write, you know, with d lambda d mu, d lambda, and write in terms of lambda. You could do that, and then the whole problem is, again, one differential equation for 3 variables in terms of 1 variable. And in fact, that's sort of what is also done in B physics. Instead of writing in terms of mu, you typically write it in terms of the strong coupling constant beta function. That's the main culprit for the running in that case. And maybe you learned about that last week. But yeah, fair point. And in practice, people do actually rewrite this in terms of other variables. But yeah. Right. Yeah, so this term will contribute to, what does it look like? Well, just 2 legs going out, either the renormalization of the field, and those set factors we'll have to call phi some phi renormalized times z, where z will be 1 plus 1 over epsilon with c 6 over lambda squared, whatever that is, or corrections to the math. And while this looks like an important term, and it will filter into, for example, the RG for lambda itself, for the quartic, for the high dimensional operators, this happens to be a higher star phi cube to the renormalized one. Square root as is equal to r with 3 powers of z, but that is 1 plus for the 1 over lambda squared. And these guys already come with a lambda squared up front. So field renormalization for these high dimensional operators and that correction proportional to 1 over lambda is a second order effect. We don't have to worry about that one. But this would have to be accounted for in the RG for lambda itself, the quartic. Right, so then we're left with one only other diagram, but this is the mountain. Okay, let's see why is that somewhat complicated. I will go with some loop integral. There's two propagators, but in here we cannot neglect the external momenta. Let me write this sketchily as L squared plus, what did I write? P squared. Two propagators, but also that term, effective term depends on momenta itself. So there will be also an L squared, maybe an L dot K, and a K squared term up on top. Okay, I'm not doing the integral, I'm just trying to see what it looks like. Now the reason I cannot neglect those denominator momenta in there is because, yes, there's this first term, that is external momenta k squared over 2 powers of the propagator. That will give me a logarithm, and I'll get a k squared. And 1 over epsilon for pi, whatnot. Now the term proportional to L, what do you think happens to it? 0, because it's odd, and we integrate them from plus to minus infinity. So off it goes. And then the term proportional to L squared, you might think, well, just dimensionally, that is going to be proportional. So 4 powers of L in here, 4 powers down here, and 2 powers up there. The final answer should be dimension 2. However, we do this integral, there's only one scale in the problem, or in that term. So that will be proportional to p squared. So we also have to do that integral there for that, keeping p squared general. The external state momenta, and that means doing two types of loop integrals, but when we sort of put the two propagators in terms of 1 squared, we have to use Feynman parameters. Then we have to shift the loop momenta so that it's truly even in the denominator and carry on. I don't know how deep into loop computations Anish and Matthias went, but that's the standard procedure. And again, it's in books, and it's sort of sketched in the notes. But then for the last bit of, and it's good because we're also sort of out of time, for the last bit of features of this computation that are not as easy to spot, is that even you've done the computation carefully and you computed these two terms, they'll be in terms of the momenta of the external particles in here. And again, looking at the external x in this term, you'll have to get something with 4 fields. And by the look of these, two derivatives. Right, so you have to decompose this again into contributions to CS, CG, but nobody guarantees that the outcome of this computation will be only those two operators. Because, well, after it's a loop computation, it's at the quantum level, and the physics doesn't care about the basis you chose. You will just produce whatever can produce out of that term. In particular, you could get out of this that very operator we wrote in the second lecture that we got rid of. And if that operator is produced, it's no biggie. Well, we have to get rid of it just like we did at the tree level. It was not in our original basis. Now we're doing the theory at one loop. So this comes with a one loop term, etc. But it's not in our original basis. So, and we're working to get to 1 over lambda square. We can use the same procedure to remove this. But remember, we remove this at the cost of a contribution to C6. You can go through the notes again. So this, even though it looks like it's this diagram with 4 external legs, through this equation of motion is secretly, again, a contribution to C6. Right? So that's why I wrote a bar in here, because proportional to CS and CG, but via the equations of motion, there's another contribution in here, possibly. I haven't computed it. Let me call it EOM. And there could be another one coming from CG. And it's only the sum of the two that is the physical thing. And even though this looks like, and it is a technical point about EFTs, it is also, the way to do things systematically. So if you're a bit confused by this, how do I know if there's such a contribution or not? Well, what you have to do is what we did in the beginning. Draw all of the UV divergent diagrams with one insertion of your operators. As long as you've done that, you save, you compute all of those UV divergences, you analyze where would they come from. Some of them will give higher order effects that we can safely neglect. But after finishing this procedure and finding those operators, you might have that the one loop has generated new operators you didn't have. Don't panic. Shift them back to your original basis, whatever the basis was. Again, this is a basis independent statement, and you get the RG in full to that level. Now, the point where there's some interesting physics in this is that once you've done this and put all of the terms and computed sort of the physical sum of all of them, one sometimes finds that some of these entries cancel after you put everything together with a very non-trivial set of terms coming together to give you a zero. Now, whenever we see a zero in physics, we think, well, symmetry must be something there. I've been a little silly and didn't realize there was a symmetry that told me this operator has some properties different from this other one, and that's why they wouldn't mix. And that indeed can be used, and it will tell you that some entries in this might be zero. But it was also found that some other entries had no symmetry reason, evident symmetry reason to cancel in this RG computation of the standard model. And at the time, this is not more than 10 years ago, we had no clue what that happened, so we just pointed it out. It was afterwards with helicity methods, actually, that we figure out why some of these entries cancel. It's related to some selection rules in helicity. There was a paper at the time by the group in Caltech, Clifford Chong and his student, that looked at this. Also at the time, Alex was thinking about it, and that's so a new piece of physics that came out of this. I'm not sure if you'll have time, Alex, to talk about these cancellations. Yes. So yes, Alex will tell you more about those and how they come. How you can see them in helicity method, and they're not evident from the field formulation. And yeah, and I think that's that's all I wanted to tell you. There's more things for you to dig into, problems in the notes, and more references for where to see some of these papers that put out these results and the discussion. I just put a few references. I can put more if you like, but that should be enough to get you started. And that's, I think, a good point to close the lectures and bring things together. So let's take questions now. So you mean this diagram? What drops in here? Sorry, so this. Yes, there'll be a mass term. Yeah, so that's good. What is that going to look like? That has again two two terms, coming from propagators. In this case, these are lambdas and that's constant, so there's nothing in there. So that's just going to be the C6 over lambda squared and a power of lambda. And this is going to give me a contribution to the coefficient of six legs in there. So this itself, at the end of the process, going to have to contribute that at something that at tree level was C6 over lambda squared. Yeah, so I've not been careful with this. So that will be coming out of using Feynman parameters, putting this into one term, and summing this. So what I'm telling you is in this case, because we're looking at the UV divergences, we can just, don't worry too much about that. You can do it carefully and you'll get the same answer. There's also a mass term in here. Yes. There would be, yeah, but those will be subleading, they'll be higher dimensional operators, because this, again, dimensional, if I look at this, there's two propagators, forget about exactly what p's flow through them. There's two propagators, there's an integral over d for L, and there's a coefficient 1 over lambda squared. If I count dimensions in here, that already has dimensions of 1 over energy squared. Yeah, you would have, yes, you can have log mu over, if you do it carefully, the Feynman parameter resummation will give you a combination of p squared and m squared, and that will come in here. Yeah. Yes, no, it's true. And I mean, even more subtle for the, this is going to be a different combination for momenta for each of the different possibilities for those. So what the RGE group is doing, which is what we're focusing on, is not worrying about those special different kinematics. You can have ST in here. It's just worrying about the overall scale of the process. So it's resumming terms that get large, or logarithms that get large when you change the whole scale by a large shift. So those subtleties, or not subtleties, but all the kinematic information will be that p squared and m squared that you mentioned. What we're doing is resumming the overall scale shift in this. That comes from, again, this. So the RGE only makes, well, it makes sense in other cases, but it's most useful when you have a large scale separation between the UV and the IR, because you're summing logs that are potentially very large. Yeah, but thanks for the question. Mm. Yeah, block diagonal entries. Yeah, so you can, there's a number of things you can do, and we tried at the time. There's one quote unquote simple thing that is draw all the diagrams. Don't compute it, but just draw them. And sometimes, for example, you have that if you put in fermions, let's say we have fermions. I'm using the same lines, but that's confusing. But you can have a 4 fermion operator and the very operators that we consider with scalar. You know that at the one loop, what you can do with these guys, you can close the loop, the fermion loop, for example, with another. You can close this and produce a 2 scalar. But you cannot close both fermion loops at the same time, and you cannot have that at 4 fermion operator at the one loop level give you something like looks like 4 scalar. Just purely drawing one loop diagrams, you realize, well, maybe this cannot contribute to that. It's just not at this level in the loop expansion. Then you can use what we call a spurion analysis. So some operators might break some symmetries that are preserved by the leading order Lagrangian. That would be flavor, for example, in the standard model, or others. And that spurion analysis will tell you which operators are not likely to mix. Because, for example, if a symmetry is not broken, that flavor symmetry is not broken, as is the case of all of the scalar operators, they could not produce flavor breaking terms in the form of 4 fermion operators. So that's spurion analysis for symmetry. Then there's a sort of automatization of that loop. That loop drawing and looking at what can contribute to that. It uses a bit of graph theory and the fact that the number of external lines plus internal plus loops adds up to something that can be cast into what is known as naive dimensional analysis. The thesis topic for a niche back in the 80s. And I will tell you about something else about these possible entries. And then today we know we can add to this list those helicity selection rules, which very roughly speaking tell you that an operator with a high helicity, for example, a 3-point vertex that has all of the gauge boson with minus helicity, will typically not mix with operators with less helicity, purely scalar, for example. But the details are in the papers, and you'll hear a bit more about that in 30 minutes. Thank you.